All right, last time we were talking about these link structures. And these link structures, they're made up of a series of nodes, and these nodes are very simple objects. They're objects that are typically going to hold some data, and they're also going to have a pointer to another node of the same type. That's it. So here's a nice representation. Think for a second. Remember, head itself is the pointer, not the head node. That's important. It's a pointer that gets us to the head node, but remember that they're separate. So if you think for a second, so last time we were talking about how to add things to the middle, add things to the end, add things to the beginning. How would I go about removing something from the beginning in this situation? How could I remove that? Let's not worry about getting the data at this stage. We can add that in later. How would I just make the head the next thing?
Create a new one and point it to the head.
Say that again?
Like create a new pointer and have it pointing to the head.
So create a new pointer, call it like new pointer, and set it to point to head.
Yeah.
But now I just have two pointers pointing to the thing at the beginning. What do you think?
Have head point to the second object and then delete the pointer to the original.
Yeah, so we're probably going to want to have like a pointer keeping track of the old head. Then set head equals head get next, and then delete the original head, lest we get some memory leak. Okay. Take a minute, think, maybe talk amongst yourselves. How would you remove something from, this is the front of the list, from the middle of the list? How would you remove something from the middle of this list? Talk amongst yourselves. Think about this for a second. It's too quiet. You can talk. I want you to talk to each other. And then how about the end? How would you remove something from the end? Again, just talk amongst yourselves, see if you figure this one out. All right, so let's go through some examples. Yeah?
Do you think you could briefly go over like what a memory leak is and like when it would occur?
A memory leak, perfect example of this. So a memory leak is when we've allocated memory that we have allocated. You look for a new keyword. Whenever you use new, we're allocating something to dynamic memory. And whenever we use new, it's our responsibility to free up that memory once we're done with it. So, assuming these nodes are dynamic memory, I have head here. Okay. So presumably that thing, that leftmost node there, was created with a new keyword. So that exists in dynamic RAM. Then if I said head equals head, get next. So head now points to the next one. So I have I now have a memory leak, assuming that there is no other reference to this. Because here's what happened. This was allocated. It exists in RAM. Now, I have no way to get back to this. I cannot possibly get to this I don't know where it is in RAM. The only way I can find it is if I do some sort of linear search through RAM. No, that's not happening. So I have no way to get back to this. This is a memory leak. It was allocated, and it never got deleted, and now it exists in RAM. It's taking up space, and we're just wasting space. That's a memory leak.
So you would delete that before you point to the next one?
What I would probably do is create like a new one, to del, point it to head, then say head next, head equals head get next, then delete this, and then this disappears, and we're all good.
Okay.
That's all. I guess this. There. Good question. So let's add to the front of the list. Here's my situation. I want node points to the new node to be inserted, head points to the first node in this, I said linked list here, I don't like that name, we're going to call it a linked structure. The reason I don't like this name is later on in the course we're going to learn about a linked list, which is a separate thing. So I want this blue one to become the new head. So here's what I'm going to do. I'm going to say node, set your next to head. And then where should I put head? Like that. Head equals node. Done. It points to that new one. There. There. Now it's at the beginning of that link structure. Any questions about that? Who here thought that's too easy? Yeah.
I just had a question about like pointers. Like the pointers themselves aren't in dynamic memory, right?
The pointers, okay, well it depends. A pointer is just going to be like the variable that points somewhere. So the node, like these nodes have pointers. So the node has two attributes, the data and the pointer. That pointer will effectively be in dynamic memory because it's within the dynamically allocated node, right?
Yeah.
But yeah, but it's not like, don't think of them as an object. It's a pointer to perhaps an object or who knows what.
So like head wouldn't be in, or would it?
Head? Oh, in this case, head is probably not that. I mean, it could be. Yes, no, it depends. If you, well, okay, no, head won't be. No, head would probably not be dynamically allocated, but it could be existing in something that was dynamically allocated, if that makes any sense.
Yeah.
We're going to see a bunch of examples of this as we go, and it's probably going to clear up as we see more and more examples. Yeah. Did you have a question?
Yeah, would you want to delete node afterwards, or would that delete its, like, the blue one as well?
Exactly. If we delete node, that pointer isn't what gets deleted. It's the thing that the pointer points to that gets deleted. And if we did that, suddenly we would delete the blue thing, and now head points to nothing. That would be very bad. Let's add something to the middle. So here's the node I want to add. Here's my link structure. Let's insert the new node after the third node in this linked list. 1, 2, 3. So I guess I want it between the bluish and the black one. There. So how am I going to do it? I'm going to have to get some sort of pointer to the one that I want to insert it after. So I've got current here. Think for a second. Obviously, what I'm going to have to do is update these pointers. That's not a mystery. But take a second and think, because the order is going to be very important. What happens if I say current set next to node? Excuse me.
You'll lose the black one.
Bingo. We're going to lose the black one. Because suddenly this will point to that blue thing, but now what points to the black one? Nothing. We're big trouble, we lost reference to that object, inadvertently creating a memory leak as well. So that would be very bad. So the order here really matters. I'm going to have to then say node set next to currents next, then current set next to node. Yeah,
When you lose the blue one then?
the blue one?
Like, if node was being set to,
Nope. Nodes next
oh,
is being set to currents get next.
okay, yeah,
Exactly, good question.
yeah.
So node is left alone, but the thing that nodes points to, what that one points to, is being changed. So if the order here matters, there, we end up in this situation. Adding to the end is basically, we saw that into the front with the special case. Is that in the end a special case? Well, kind of, but not really, because what is the black one's next? Null pointer, exactly. So it's adding to the end is actually basically exactly the same as adding to the middle, because we would say, imagine there was a blue one up there. Node, set your next to currents next. What's currents next, assuming this is current? No. And then this set next to node. It's actually the same. Yeah.
So what do you end up deleting like the node and the currents, like their pointers? Like do you end up deleting how node gets to the blue or how the current would get to the black here?
So ask that again in this context.
Okay, so the node is pointing to the dark blue. So after you end up getting the dark blue into the list, would you end up deleting the actual node?
You mean the node pointer?
Yeah.
No, because we don't delete the pointers. We delete what the pointers point to. So if we said delete node, it would delete the blue box, which would be very bad. So the pointers, you leave them alone. They're fine.
They don't, so that would cause a memory leak then?
No, because that's just a pointer.
Okay.
Yeah. The only way it could cause a memory leak, the memory leak wouldn't be an issue with this. It would be a much different, bigger issue depending on where those nodes are allocated. But that's not an issue for this. It goes to your question about, are they dynamically allocated? Well, they could be if they're in a container that was dynamically allocated, but
They need to be in something that's, like, in dynamic memory to be.
they don't need to be.
They don't?
No, because I could just create them in like a main. Every pointer we've used so far, I don't think we've seen.
I mean, like, to cause memory.
Yeah,
Yeah.
yeah,
Can we have two pointers to the same node?
absolutely. We could have a million pointers to the same node if we wanted.
Yeah, but if the other pointer is also part of another stack,
Say that again.
if this is a stack, right?
It's not. This is not a stack.
No, I meant like it is from head to node we are having. In the same way, if we are having another head pointing to this node.
Do you mean? Let me see if I know what you're asking. Is that what you're asking? We could do that. I wouldn't in this situation, but there's nothing stopping us from doing this. Whenever you ask the question, can we do this? If you're following the rules, you absolutely can. Because you can doesn't mean you should.
But what data will it hold like in this particular one?
What do you mean with whatever data was in here?
So that data interacts for this one as well as this one.
I mean, it's the exact same node. There's only one node. We have got two link structures getting us there. There's nothing stopping us from doing this, too. We could do that. It's kind of weird to do that, but we could. Right? There's nothing wrong with that structure. So, deleting from the front. Well, here we go. Head, set it to next. Head equals head, get next. But of course, there would be a memory leak here. We're going to want to delete that head node. So we're going to need a pointer to keep track of it. Deleting from the middle. If I want to delete that, I'm going to have to find its previous. Any ideas on the easiest way to find the previous? Someone over there mentioned it a little while ago. How do I get the previous node? Yeah, it's one less. But I got to start at the beginning and keep going to the next until the next is current, exactly. So we'll do a linear search until the next one is current. And then I have a pointer to the previous. So if I want to do this, well, I would say previous, set your next to previous, get next, get next. What's previous, next, next? The black one. Good. So we do that, and of course we'll delete current to eliminate the leaps.
So how do you like iterate through then? Like, cause if you had like an equals like comparison to like what you wanted to find, wouldn't it stop on that node then?
Well,
or would it stop before it?
There's a bunch of ways I could do it. I could say, I could do like a while true. I could start my iter pointer at head while true, or I could say like while iters get next is not equal to current, go to the next.
Okay.
Deleting from the end. This is actually kind of exactly the same as deleting from the middle as well. Because what's the black's next? No. So if this was current, this was previous, what's next, next? No, it would still work the same. So there. Let's actually implement this class now. We talked about it, but we never actually implemented anything here. So let's actually see how one could implement this. So here is the header. I know I showed you this already before, but here we go. Two private attributes. In this case, this is an int node, remember, and it's going to be a pointer to an integer. So we've got this int, pointer, data, and int node, star, pointer, next. So it's got the two attributes, and we've got our constructors and our getters and setters. That's it. A very simple class. So here's one of the constructors. There. Easy. The default constructor just set its values to like nothing to start. Null pointer, great, we're all set. Here's one where we actually give it a pointer to an integer. There. Basically exactly the same, but we just assign the data to whatever we pass to it. That's it. Yeah.
Why do we have to define next as null pointer if it's already defined in the default constructor?
But because only one of the constructors, it's not being redefined. It's which constructor is being called. There's two of the constructors we can call so far that we've seen, the default and the not default. If we call the constructor that takes no parameters, it's going to run those two lines of code. If we call the constructor that takes a parameter, it's going to run this one. And we're not redefining. We're just running one or the other. Yeah. Copy constructor. All right, great. Copy over there. Done. Nothing like stacks. We'll assume these are pointers to important things, and we'll just trust that the programmer will delete what they don't need anymore. So similarly, remember how with stacks? Also, again, I should emphasize, this is not like an alternative to a stack. That's not what we're doing at this stage. But because this is just like a container, think of it like when you delete an array. If you delete an array, C++ isn't going to go through and make sure that you delete all the contents of the array if they were dynamically allocated. It's not going to do that. You would have to loop through it delete all the things, then delete the array. Same idea here. Well, we'll delete the node, but I'm not responsible for deleting like the data in the same way that the array wasn't. So get data, return the data. Set data, set the data. Get next, set next. That's it. That's it. That's honestly it. So we're going to be putting this to use very soon. At this stage, you're scratching your head thinking, okay, but why? Well, later we're going to, remember how we just built a stack with an array? We will build a stack with this link structure. And then as we are going through it, we're going to look at the pros and cons. One implementation versus another. Why is this one good in that situation? Why is this one good? And we're going to talk about computational complexity. So we're going to use this. But for now, let's just do some testing. So here we go. Int node head equals a new int node, and I'm giving it the new integer. So there's two constructors. Which constructor am I calling? Well, the one that's not the default one. And I create a new pointer n that also points to head, I guess. And what am I saying? Co n get data. If I were to run this, what would the output be? Come on. 0. How about this? Look at this code. What the heck's going on here? Assume n is also starts pointing at the same thing head points at. What's going on here? Take a second, think about it. Talk amongst yourselves. See if you can figure this one out. Alright, let's go through this. Also note, I'm going to draw the numbers inside the nodes, even though that the numbers are actually pointers. That's probably too small for anyone to see at the back, eh? I'm going to draw the numbers inside the nodes, despite the fact that they're actually pointers, just for simplicity. So this is our current situation before running this code. So what am I saying? For I 1 to n, or to 10. Okay, great. And set next to a new node with the integer I in it. Okay, so your next is going to be set to a new node with the integer of what I is. Well, that's 1. And then n, n equals n, get next. Okay. So don't point that. There. Great. I plus plus. Now I is 2. Oh, n. What's n? Oh, it's a pointer to this one. Set it's next to a new node, the number 2 in it, and then update n. When this code finishes running, what will I have? 10 elements, 0 to 9 in this link structure. There are all these nodes pointing at each other and everything. Yeah. Okay, good. I got different variations of snippets of the answer. Good. What's this going to do? I set n back to head. Talk amongst yourselves. to 9. Actually, for simplicity, we'll just go to 2. We start here. And I ask the question, is n null pointer? No. Okay. So print it out, and then n is next. We go back to the top. Is n null pointer? I guess I should be asking, is n not null pointer? True. Great, so print it out. Is n not null pointer? True. All right, print it out. N is set to n's next. What is this one's next? Null pointer. Good. So this points to the same nothingness. Then I ask, is n not equal to null pointer? False. Oh, I stopped. Done. Good. Yeah.
I just I just don't seem to quite grasp what n is.
N is just another pointer, another int node pointer. That's all it is. In fact, let me just go back just to make sure you don't think I'm crazy.
So n
That's
is
it. It's just an int node pointer, and it's just another pointer. And head and node after these two lines of code are pointing to the same object.
So n technically is imperative to the like structure, like head.
It's not. It's just another pointer. In theory, I could start moving head around and leave n at the beginning. But that would be very, very bad convention because head is usually the pointer that gets us to the beginning.
So n is for like utility, head is for structure.
Bingo. N is like an iterating thing. Yeah. You had a question?
What was the point of like the dereference?
The dereference?
At like
In here?
and get data.
Because n get data returns a pointer to an integer.
Okay.
And then we need to actually get that integer. That's all. Do you believe me?
Yeah.
Okay. You had a question?
yeah. So like n isn't pointing to head; it's just pointing the same thing that head's pointing to.
Yes. So it's not that I'm copying over the contents of head.
Okay.
And what's the contents of head? It's an error to this thing. So it's not this. No. It's copy. Oh, it's just. Yeah.
I'm not sure if this is the same question that he just asked, but in the previous slide, where it defines int node n, wouldn't that int star node, or int node star n equals head, wouldn't that mean that n is pointing to head?
No. It copies. Remember, whenever we see an equals, it copies over the contents of that variable. What's the contents of head?
Pointer.
Nope. It's a pointer to it. It's the memory address of where that int node is. So when I copy over the contents of that variable, it's just the memory address where that int node is. I copy over that memory address to where the int node is to n. So now I have two variables with the same memory address, two pointers to the same thing.
So if you didn't have the star next to the int node before the n, then what would that do?
That wouldn't work because I would need to like dereference head in order to get it to work. Because int node, that's a variable that's going to be an int node. But head is a pointer to an int node. Yeah. You gotta watch our types. Super careful. Doubly linked lists are absolutely a thing. There's nothing stopping us for doing this. In this case, I can get to any nodes next and any nodes previous. Basically, each doubly linked list node has three things: the data, its next, and its previous. There's nothing stopping me from doing this. We're not going to be talking about these really anymore in the class. But the adding and removing at the beginning, middle, end, it's basically the same thing, but we have to make sure we're updating all the pointers correctly. Like if I remove the middle one, I have to update this one's next and this one's previous. You know, I just got to be careful with those pointers. Cool. Cool. Any last questions? All right. So, So on lab last week, during lab last week, I gave you the code to an int stack, right? An int stack was a stack full of like integer pointers. But what did I make you do? Change it to a character stack. What if I gave you the int stack and said, well, make a string stack? You could do that, right? What if I asked you to make a double stack? You could do that. What if I wanted to make you do like a stack stack? A stack full of stacks? I mean, you could do that. It'd be kind of weird, but yeah, you could totally do it, nothing's stopping you. What about a Boolean stack? If I gave you the int stack, could you make a Boolean stack? Booyer thinks this is kind of silly though. You need to make a new, you do, yeah? You need to make a new stack. You need to write the code to create a new stack for every new type you want to add to that stack. Who finds that annoying? I do. Well, I got good news. We can fix this. So, we're going to see what generics are and why they're awesome. See how to implement them by making a generic node class. And see why we annoyingly have to write code in the header now. Okay, so remember before how I was saying the header is basically where you define everything, and the CPP is where you basically write the code how to do everything? Well, throw that away now when we're doing generics. And it's funny. I'm going to explain why as we go, but long story short, when we do the generics, we are actually creating what we call templates, and we don't write the code for how. CPP file still has all the code for how, but C++ will generate the code for you based on the templates we're about to write for the generics for the specific type. You'll see. Here was our int node, right? This should look very familiar considering we just finished talking about it. Great. Character node. If I wanted a character node, I would do this, right? Right? Nothing crazy. What if I wanted a double node? I would do that, yeah. Is this not annoying? Yeah, it certainly is. We already established this. There's got to be a better way. There is. Here's what we're going to do. Take a look at this, and what do you notice that's a little bit different? Take a second look at it. Just give yourself a second to observe what's different. All right, someone point out one thing different. Yeah.
The type for a lot of stuff is just T.
The type is T. Yeah. Anything else different? Yeah.
The template class T at the top.
Template class T. Yeah. Anything else? I mean, that's basically it. So the generic is kind of like a variable for the type. What if I can write the code in a way that says B code for a T type node? Then when I implement it, when I use it, I can be like, okay, I want T to be a character. Or maybe I want T to be a character pointer. Or maybe I want it to be a double pointer or an int. I can do whatever I want. So when we say template class T, that's like telling C++, okay, this is generic. Then, because the type isn't known yet, it's just a variable. But T is like the special thing that we use. I'm pretty sure in C++, it doesn't have to be T. T is just like the convention. T is a stand-in for the type. So, what's the type of the data in this stack? Or pardon me, in this node?
T.
T. I don't know what it is yet. But whatever it is, it's going to be T. Then when I get data, what's it going to return? something of type T. Well, what is T? I don't know yet, but it's going to be T, whatever it is. When I set data, it needs to be of type T. Here is, pardon me, here's how I would use it. But of course, type, you would actually put in the type you want. So for example, if I wanted to make, in that int node as before, where the type was integer pointers, this is how I would create it. That's it. Now, I've got a generic node. So, it's of type node, but the thing in those like triangle brackets, the less than and greater than sign, that's the type. So, if I were to run this, C++ knows, oh, T, that's an int pointer. That's what it would be. Basically, all the places where you would see T gets replaced with its pointer. If I want a character pointer, that's how I would do it. Double pointer, that's how I do it. Boolean pointer, that's how I do it. Just an integer, like not an integer pointer, but an integer, great, that's how I do it. A regular character, that's how I do it. Pretty cool, huh? So how do we make it happen? Well, we need to define a template. It's kind of like a framework for what the possible types they're going to be. So this is easy. Then C++ is actually going to look at the template, and the template's usually going to be written in your header file. It's going to look at the template and then generate the code, basically like a copy-paste, find and replace all T's with whatever type you put in there, and generate the CPP code for you. So a lot of times that CPP file is going to be like empty. Yeah, so it generates it for whatever the type is. So how do we make it happen? So where do we write the templates? In the header. This is probably going to annoy you because it's before I was saying, well, you say the what and the how, you kind of separate between header and CPP. You're absolutely right. It annoys me too. But you can kind of think about it like they're templates. When we write the template stuff in the header, the template isn't really the how. It's kind of like how to generate the how. At least that's what you can tell yourself to feel better. Okay, so here's the code. Who can read this? Nobody. So let's, of course, jump into it a little bit better. So this is now the new node.h file. Obviously, you can't read it. Okay, so we're going to start with this. This is what we saw before. I'm lucky I made it this far without coughing up a storm. But this bit is new, and it's going to look a lot like our int node class. So, here's node.h. This is what we just saw a second ago, with the T in place of everything else, but also that template T. Now, all the stuff we're about to see gets added below here in the header file. Generic default constructor, there. I have to write template class T above it, node T : node. But it's a default constructor, so it's very simple. Now, I put 0 here because data, the thing of type T, might not be a pointer. So I don't know if I can set it to null pointer, so I'll set it to 0. Basically, is it an integer pointer or an integer? I don't know. It's T, it's up to you. But next is always going to be a pointer. It's always going to be a pointer to a node. Here's the not default constructor. Same deal. We put that template thing at the beginning. Yeah?
So you have to put it above all the constructors?
So you would put it above basically like everything. It doesn't actually have to be above. I'm pretty sure you can put it on the same line, but it's just a convention to put it above. I'm not 100% sure, to be honest. Yeah?
In the generic constructor, when you initialize data to be 0, since you don't
So 0 is going to be cool for like all those types, because 0 is also like a special thing that means like not.
Okay.
Yeah.
So what about the methods? Do you have to put above the methods as well?
Well, let's have a look. Copy constructor, okay, it's same thing. Deconstructor, same thing. Yes. Your getter, set. Get, set. Want to see what, this is what the CPP file looks like. Include node.h. That's it. That's it. So you say, okay, you said that we just say what in the header and how in the CPP file. Yeah, but here's the thing. In this example, did we ever tell CPP how to act for a node class that's type int or anything? No. We defined the template and then C++ generated it for us. So here's an example of me using it there. This is a type integer pointer, then there's a type integer, and then I do, ooh, here's a weird one. What's the type of this node? Its type is a node of type int. Weird. I can do that. Anyways, see you tomorrow.